Remember, we are one unit, fighting with one goal. The village. We have to protect those people. That was close.
The Erusians, but we can't take him down.
I got it. I'm gonna power kick that orb thing.
No, the last time you did a kick, we fell.
Stop living in the past. Oh no!
Pidge, fire lasers now!
Got it! Fire! Oops!
No, lasers! Lasers!
Every time we focus on that orb, we're blindsided by the monster. And every time we focus on the monster, the orb hits us. We can't take much more!
Last one! Everyone, brace for impact! Now!
What if the data doesn't lie in a two-dimensional, three-dimensional, or so even a finite dimensional space? But is it possible? What if your data actually lies in an infinite dimensional space?
It didn't work!
So now what?
When I attacked him before, I had a sword!
Orb! Orb!
We can't take another shot like that!
Wait a second, guys. I think my lion's telling me what to do.
Well, whatever it is, hurry up and do it. He's about to fire his third shot.
How did you do that?
Lady Jaina, it is a pleasure to fight by your side once more.
Thanks, Red.
No idea how much we've missed your counsel.
I'll make another, more powerful.
That won't be necessary. Sendak is still alive on Eris. I've given him instructions for how to proceed.
Can he be trusted?
I trained him and he has his mission. He fights in the name of...
Right, I plotted here a two-dimensional space. I can't plot to an infinite dimensional space, right? And so it turns out that one of the most successful classes of machine learning algorithms, something called support vector machines, actually takes data and works and maps data to an infinite dimensional space, and then does classification using, not two features like I've done here, but an infinite number of features. And that will actually be one of the most fascinating things we talk about when we go deeply into classification algorithms. It's actually an interesting question, right? So think about how do you even represent an infinite dimensional vector, in computer memory? You don't have an infinite amount of computers. How do you even represent a point that lies in an infinite dimensional space? Okay, we'll talk about that when we get to support vector machines. Okay. So let's see. Well, so the second of the so that was supervised learning. The second of the four major topics of this class will be learning theory. So I have a friend who teaches math at a different university, not at Stanford. And when you talk to him about his work and what he's really out to do, this friend of mine will. So he's a math professor, right? This friend of mine will sort of get the look and wonder in his eyes, and he'll tell you about how in his mathematical work, he feels like he's discovering truth and beauty in the universe. And he says it in sort of a really touching, sincere way. And then he has this, you can see it in his eyes, he has this deep appreciation of the truth and beauty in the universe as revealed to him by the math he does. In this class, I'm not going to do any truth and beauty. In this class, I'm going to talk about learning theory to try to convey to you an understanding of how and why learning algorithms work, so that we can apply these learning algorithms as effectively as possible. So for example, it turns out you can prove surprisingly deep theorems on when you can guarantee that the learning algorithm will work. Right? So think about learning algorithm for reading zip codes. When can you prove a theorem guaranteeing that the learning algorithm will be at least 99.9% accurate on reading zip codes? This is actually somewhat surprising. We actually prove theorems showing when you can expect that to hold. We'll also delve into learning theory to try to understand what algorithms can approximate different functions well and when, and also try to understand things like how much training data do you need? So how many examples of houses do I need in order for your learning algorithm to recognize the pattern between the square footage of a house and its housing prices? And this help us answer questions like, if you're trying to design a learning algorithm, should you be spending more time collecting more data, or is it the case that you already have enough data and it'd be a waste of time to try to collect more? Okay, so I think learning algorithms are a very powerful tool, but as I walk around sort of industry in Silicon Valley, or as I work with various students in CS and outside CS, you find that there's often a huge difference between how well someone who really understands this stuff can apply a learning algorithm versus someone who, you know, sort of gets it but sort of doesn't. The analogy I like to think of is think of if imagine you were going to a carpentry school instead of a machine learning class. Right? If you go to a carpentry school, they can give you the tools of carpentry. They give you a hammer, a bunch of nails, a screwdriver, or whatever. But the master carpenter will be able to use those tools far better than most of us in this room. So I know a carpenter can do things with a hammer and nail that I couldn't possibly. And it's actually a little bit like that in machine learning too. One thing that's sadly not taught in many courses on machine learning is how to take the tools of machine learning and really, really apply them well. So in the same way, so the tools of machine learning are, you know, I want to say quite a bit more advanced than the tools of carpentry. Maybe a carpenter will disagree, but so a large part of this class will be just giving you the raw tools of machine learning, just the algorithms and so on. But what I plan to do throughout this entire quarter, not just in the segmental learning theory, but actually as a theme running through everything I do this quarter, will be to try to convey to you the skills to really take the learning algorithm ideas and really to get them to work on the problem. It's sort of hard for me to, you know, stand here and say how big a deal that is. But when I walk around companies in Silicon Valley, it's completely not uncommon for me to see someone using some machine learning algorithm, and then explain to me what they've been doing for the last 6 months, and I go, oh, gee, you know, it should have been obvious from the start that the last 6 months you've been wasting your time, right? So my goal in this class, running through the entire quarter, not just on learning theory, is actually not only to give you the tools of machine learning, but to teach you how to use them well. And I've noticed this is something that really not many other classes teach. So, this is something I'm really convinced is a huge deal. So, by the end of this class, I hope all of you will be master carpenters. I hope all of you will be really good at applying these learning algorithms, and getting them to work amazingly well on many problems. Okay. Let's see. So, some of these slides out of order. After learning theory, there's another class of learning algorithms that I then want to teach you about, and that's unsupervised learning. So you recall, right? Well, on the a little earlier, I drew an example like this, right, where you have a couple of features, a couple of input variables, and so malignant tumors and benign tumors or whatever. And that was an example of a supervised learning problem because the data you have gives you the right answer for each of your patients. The data tells you this patient had a malignant tumor, this patient had a benign tumor. So it had the right answers, and you wanted the algorithm to just produce more of the same. In contrast, in an unsupervised learning problem, this is the sort of data you get. Okay. Where, speaking loosely, you're given a data set, and I'm not going to tell you what the right answer is on any of your data. I'm just going to give you a data set, and I'm going to say, would you please find interesting structure in this data for me? So that's the unsupervised learning problem, where you're sort of not given the right answer for everything. So for example, an algorithm may find structure in the data in the form of the data being partitioned into two clusters. So clustering would be one example of an unsupervised learning problem. So you can see this. It turns out that these sorts of unsupervised learning algorithms are also used in many problems. This is a screenshot. This is a picture I got from Sue Lee, who's a PhD student here, who's applying unsupervised learning algorithms to try to understand gene data. So it's trying to look at genes in individuals and group them into clusters based on properties of what genes they respond to, based on properties of how the genes respond to different experiments. Another interesting application of these sorts of clustering algorithms is actually the image processing. This picture I got from Steve Gould, who's another PhD student. It turns out what you can do is if you give this sort of data, say an image, to certain unsupervised learning algorithms, they will then learn to group pixels together and say, gee, this set of pixels seem to belong together and that set of pixels seem to belong together. And so the images you see on the bottom, I guess you can just barely see them. So the images you see on the bottom are groupings, are what the algorithm has done to group different pixels together. On a small display, it might be easier to just look at the image on the right. The two images at the bottom are two sort of identical visualizations of the same grouping of the pixels into contiguous regions. And so it turns out that this sort of clustering algorithm, this sort of unsupervised learning algorithm, which sort of learns to group pixels together, it turns out to be useful for many applications in vision, in computer vision image processing. Let's show you one example. This is a rather cool one that two students, Ashutosh Saxena and Min Sun here did, which is given an image like this, right? This is actually a picture taken on Stanford campus. You can apply that sort of clustering algorithm and group the picture into regions. Yeah, let me actually load that up so we can see it more clearly. Okay, so in the middle you see the lines sort of grouping the image together, grouping the image into contiguous regions. And what Ashutosh and Min did was they then applied the learning algorithm to say, can we take this clustering and use it to build a model, to build a 3D model of the world. And so, using the clustering, they then had a learning algorithm try to learn what the 3D structure of the world looks like, so that they could come up with a 3D model that you can sort of fly through. Okay. By the way, many people used to think it's not possible to pick a single image and build a 3D model. But using a learning algorithm and that sort of clustering algorithm is the first step. They were able to. I'll just show you one more example. I like this because it's a picture of Stanford, of our beautiful Stanford campus. So again, taking the same sort of clustering algorithms, you can, taking the same sort of unsupervised learning algorithm, you can group the pixels into different regions. And using that as a pre-processing step, they eventually built this sort of 3D model of Stanford campus in a single picture. So you have to walk into the scene, look around the campus. Okay. This actually turned out to be a mix of supervised and unsupervised learning, but the unsupervised learning, the sort of clustering, was the first step. So it turns out
Find something else to fight over.
there are these sorts of unsupervised clustering algorithms are actually routinely used for many different tasks. Things like organizing computing clusters, social network analysis, market segmentation. So if you're a marketer and you want to divide your market into different segments or different groups of people to market to them separately. Even for astronomical data analysis and understanding how galaxies are formed. These are just a sort of small sample of the applications of unsupervised learning algorithms and clustering algorithms that we'll talk about later in this class. Just one particularly cool example of an unsupervised learning algorithm that I want to tell you about. And to motivate that, I want to tell you about consider what's called the cocktail party problem, right? Which is, imagine that you're at some cocktail party and there are lots of people standing all over. And you know how it is, right? If you're at a large party, and everyone's talking, it can be sometimes very hard to hear even the person in front of you. So imagine a large cocktail party, lots of people. So the problem is, if there are all of these people talking, can you separate out the voice of just the person you're interested in talking to, right? Because with all this loud background noise. So I should show you a specific example in a second. But here's a cocktail party that's, I guess, rather sparsely attended by just 2 people. But what we're going to do is we'll put 2 microphones in the room, okay? And so, because the microphones are just at slightly different distances to the two people, and the two people will be speaking at slightly different volumes. Each microphone will pick up an overlapping combination of these two people's voices, but they are slightly different overlapping voices. So speaker 1's voice may be more loud on microphone 1, and speaker 2's voice may be louder on microphone 2, whatever. But the question is, given these microphone recordings, can you separate out the original speakers' voices? So I'm going to play you some audio clips that were collected by Taewon Lee at UCSD. Let me actually play for you the original raw microphone recordings from this cocktail party. So this is the microphone 1.
1, 2, 3, 4, 5, 6, 7, 8, 9, 10.
So it's a fascinating cocktail party with people counting from 1 to 10. This is the second microphone.
1, 2, 3, 4, 5, 6, 7, 8, 9, y 10.
Okay. So remember, in unsupervised learning, we don't know what the right answer is, right? So what we're going to do is take exactly the two microphone recordings you just heard and give it to an unsupervised learning algorithm and tell the algorithm, would you please discover structure in the data for me? What structure is there in this data? And we actually don't know what the right answer is beginning offhand. So give this data to an unsupervised learning algorithm, and what the algorithm does in this case, it'll discover that this data can actually be explained by two independent speakers speaking at the same time, and it can further separate out the two speakers for you. So here's output 1 of the algorithm.
1, 2, 3, 4, 5, 6, 7, 8, 9, 10.
And that was the second output.
1, 2, 3, 4, 5, 6, 7, 8, 9, y 10.
Okay, and so the algorithm discovers that, gee, the structure underlying the data is really that there are two sources of sound, and here they are. Show you one more example. This is this is a second different pair of microphone recordings.
1, 2, 3, 4, 5, 6, 7, 8, 9, 10.
So the poor guy is now at the cocktail party where he's talking to his radio.
1, 2, 3,
There's a second recording.
5, 6, 7, 8, 9, 10.
Right, and if you give this data to the same unsupervised learning algorithm, the algorithm is actually called independent component analysis, and later in this quarter you'll see why. It then outputs the following.
1, 2, 3, 4, 5, 6, 7, 8, 9, 10.
And that's the second output. Okay. So it turns out that beyond solving the cocktail party problem, this specific class of unsupervised learning algorithms are also applied to a bunch of other problems, like in text processing or understanding functional brain imaging data, like magnetoencephalography and EEG data. And we'll talk about that more when we go and describe ICA, or independent component analysis algorithms, which is what you just saw. And as an aside, this algorithm I just showed you, right, it seems like it must be a pretty complicated algorithm, right? To take these overlapping audio streams and separate them out. It sounds like a pretty complicated thing to do. So you're going to ask, how complicated is it really to implement an algorithm like this? It turns out, if you do it in MATLAB, you can do it in one line of code. So got this from Samuel Wise at Toronto, U of Toronto, and the example I showed you actually used a more complicated ICA algorithm than this, but nonetheless, I guess this is why for this class I'm going to ask you to do most of your programming in MATLAB and Octave, because if you try to implement the same algorithm in C or Java or something, I can tell you from personal painful experience, you end up writing pages of code rather than relatively few lines of code. I should mention that it did take researchers, many years to come up with that one line of code. So this is not easy. So that was unsupervised learning, and then the last of the four major topics I want to tell you about is reinforcement learning. And this refers to problems where you don't do one-shot decision making. Right? So for example, in the supervised learning cancer prediction problem, you know, you have a patient come in, you predict that the cancer is malignant or benign, and then based on your prediction, you know, maybe the patient lives or dies, and then that's it, right? So you make a decision, and then there's a consequence. You either got it right or wrong. In reinforcement learning problems, you are usually asked to make a sequence of decisions over time. So for example, this is something that my students and I work on. If I give you the keys to an autonomous helicopter, we actually have this helicopter, you know, here at Stanford. How do you write a program to make it fly? Right? You notice that if you make a wrong decision on a helicopter, you know, the consequence of crashing it may not happen until much later. And in fact, usually you need to make a whole sequence of bad decisions to crash a helicopter. But conversely, you also need to make a whole sequence of good decisions in order to fly a helicopter really well. So let me show you some fun videos of you know, learning algorithms flying helicopters. This is a video of our helicopter at Stanford flying using a controller that was learned using a reinforcement learning algorithm. So this was done on the Stanford football field. We'll zoom out the camera in a second. You still see the trees planted in the sky. So I think this is one of the most difficult aerobatic maneuvers flown on any helicopter under computer control, and this controller, which is very, very hard for a human to sit down and write out, was learned using one of these reinforcement learning algorithms. Just a word about that. The basic idea behind the reinforcement learning algorithm is this idea of what's called a reward function. One way to think about it is, imagine you're trying to train a dog. So every time your dog does something good, you say, you know, good dog, and you reward the dog. Every time your dog does something bad, you go, bad dog, right? And hopefully over time, your dog will, you know, learn to do the right things to get more of the positive rewards, to get more of the good dogs, and to get fewer of the bad dogs. So the way we teach helicopter to fly, or any of these robots, is sort of the same thing. Every time the helicopter crashes, we go bad helicopter. And every time it does the right thing, we go good helicopter. And over time, it learns how to control itself so as to get more of these positive rewards. So reinforcement learning is I think of it as a way for you to specify what you want done. So you have to specify what is a good dog and what is a bad dog behavior. And then it's up to the learning algorithm to figure out how to maximize the good dog reward signals and minimize the bad dog punishments. So just to show you, it turns out reinforcement learning is applied, you know, to other problems in robotics. It's applied to things in web crawling and so on. But it's just cool to show videos. So let me just show a bunch of them. This robot was actually this learning algorithm was actually implemented by our head TA Zico. Programming a four-legged dog, because Sam Schreiber in this class is also working on the project, and Peter Review and Mike and a few others. But I guess this really is a good dog, bad dog. This is a robot dog. Second video on the right, some of the students, I guess Peter, Zico, Tonka, working on a robotic snake. Again, using learning algorithms to teach a snake robot to climb over obstacles. The low left, this is a kind of fun example. Arshal Saxena and Jeff Michaels use learning algorithms to teach a car how to drive at, you know, reasonably high speeds off-road, avoiding obstacles. And on the lower right, that's a robot programmed by PhD student Yirong Shen, to teach somewhat strangely configured robot how to get on top of an obstacle, how to get over an obstacle. Sorry, I know the video is kind of small. I hope you can sort of see it. Okay, so I think all of these are robots that